Hi guys, I'm Mr. Joseph, your chemistry teacher. I'm back with my lectures, and today we'll be looking at entropy. Our topic for today is entropy. And the lesson objectives, students should be able to define the term entropy as the number of possible arrangements of the particles and their energy in a given system. That's what we're looking at. And also predict and explain the sign of the entropy changes that occur during the change in state, like melting, boiling, dissolving of substances. Then during the temperature change, when there is addition of heat or removal of heat that has to do with increase or decrease in temperature, we're going to predict this and explain the sign of entropy change that occur. Then we'll be looking at generalization on entropy. We're talking about entropy in general, things we need to know when it comes to what entropy. So please, I want us to listen attentively and get the best out of today's lecture. So we're looking at entropy. When we talk about entropy, the first thing that comes to mind has to do with disorderliness. It has to do with movement, kinetic energy, haphazardness, movement of substance. So we'll talk about entropy. It's a measure of the degree of disorderliness or randomness of the system. When we talk about the system is that part of a reaction that is under investigation. That we're talking about the reactant and the product. We'll talk about what is system. So entropy is a measure of the degree of disorderliness or randomness of what is system. During chemical reaction, the degree of disorderliness or randomness for chemical reaction to take place. That leads us to what we call collision theory. That before any chemical reaction will take place, the reactant particles must collide in order to generate energy that is equal to the activation energy or more than the activation energy so that reaction can take place. So when we talk about system, we're talking about the reactant and the product. So entropy is a measure of the degree of disorderliness or randomness of a system. It can also be defined as a quantitative measure of the degree of disorder within a system. Yes, a quantitative measure of the degree of disorderliness or randomness within what? Within a system. So the higher the randomness of disorder, the greater the entropy of the system. The lower the randomness of disorder, the lower the entropy of the system. So this disorder refers not only to atoms, molecules, or ions within a system, but also to the distribution of energy between what? Between particles. When energy is distributed between particles, what happens? It results to what? Disorderliness or randomness. So, we can now define entropy as a measure of the dispersal of energy at a specific temperature. Temperature brings about increase in the degree of disorderliness or randomness within the system. So entropy can be defined as a measure of the dispersal of energy at a specific temperature. So temperature is very, very important. When you increase temperature, it's increasing the degree of disorderliness or randomness within the system. When you decrease the temperature, you're decreasing the degree of disorderliness or randomness within the system. So that has to do with what? Entropy. So entropy is a measure of the dispersal of energy at a specific temperature, which leads to what? A measure of the degree of disorderliness or randomness of a system. Still on entropy, so we all know that during chemical reaction, heat is either released from the system to the surrounding or from the surrounding to the system. There's always exchange of heat within the system and also within the system and the surrounding. So what happens? Heat can be transferred from the system to the surrounding or from the surrounding to the system. So when we talk about the system has to do with the reactant and the product. The part of the reaction that is under investigation is the system. Then when we talk about the surrounding has to do with the apparatus you are using, your beaker, your pipette, your burette, your conical flask, your thermometer. It depends on the apparatus you are using, it is the surrounding. Even the air around you is part of the surrounding. Even you yourself carrying out the experiment, you are part of the surrounding. But when we're talking about the system, we're talking about the reactant and the product. So entropy can also be thought of as a dispersal of energy, either from the system to the surroundings or from the surrounding to the system. So we say a system is a part under investigation. In chemistry, a system is a chemical reaction itself. That is a reactant being converted to the product. Let's take, for example, the system of zinc reacting with hydrochloric acid in a test tube to form zinc chloride and hydrogen releases energy to the surrounding. So the surrounding includes the apparatus, the test tube, the thermometer, the glass rod, the air around us, and you yourself. They are also what? Part of the surrounding. So entropy has to do with a dispersal of energy from the system to the surrounding or from the surrounding to the system. So still on entropy, the second law of thermodynamics states that what? A spontaneous process, a spontaneous change only occur whenever there's an increase in the entropy of the system and its surrounding. So a spontaneous process takes place as a result of what? An increase in the entropy of the system and the surrounding. When we talk about spontaneous change, what do we mean by spontaneous change? These are changes that tend to continue to happen naturally. We call them spontaneous change. It takes place without the need for work. Once started, the spontaneous change will carry on. For example, when light is applied, methane gas reacts with oxygen in a spontaneous reaction to form carbon dioxide and water, which is a photochemical reaction. So it is spontaneous. Once there is presence of light, the reaction takes place in the presence of UV light. The reaction is spontaneous because the methane continues to burn in the oxygen until either the methane or oxygen is completely used up. So for a reaction to be spontaneous, it does not need to happen rapidly. Yes, when we say reaction is spontaneous, it doesn't mean that the reaction will be very, very fast. No, it does not need to happen rapidly. Many spontaneous reactions are slow or need an input of energy to start them. So a spontaneous change is a change that tends to continue to happen naturally. We call them spontaneous changes. So based on what we've discussed on spontaneous change, that a spontaneous process only occurs whenever there's an increase in the entropy of the system and its surrounding. That a spontaneous change is a change that is likely to occur naturally. So which of the following changes are likely to be spontaneous? Sugar dissolving in water is spontaneous. The smell from an open bottle of aqueous ammonia diffusing through a room, yes, it's a spontaneous process because it occurs once you open a bottle of ammonia, diffusion takes place. Water turning to ice at 10 degrees Celsius is non-spontaneous. Ethanol vaporizing at 20 degrees Celsius is spontaneous because evaporation takes place at all temperatures. So once ethanol is exposed at 20 degrees Celsius, it will vaporize. Water mixing completely with cooking oil, it is non-spontaneous because water is a polar solvent, cooking oil is a non-polar solvent. These are two immiscible solvents, so it is not spontaneous. The limestone decomposing at room temperature is not spontaneous because at room temperature, limestone cannot decompose to form calcium oxide and carbon dioxide. So these are some of the processes that are spontaneous and non-spontaneous. So these are likely examination questions that they might ask you. So please, I want you to pay attention to these details when we talk about spontaneous changes. So we're looking at comparing entropy values, whereby entropy change is measured under standard conditions. To make any comparison of entropy values fair, we must use the standard conditions. Now, these standard conditions are the same as those used for entropy change of reaction. So what are the standard conditions? When we measure entropy at a pressure of 100 kilopascal or 100,000 pascal, a temperature of 298 Kelvin or 25 degrees Celsius, then each substance involved in the reaction is in its normal physical state, solid, liquid, or gas, at 100 kilopascal or 100,000 pascal and 25 degrees Celsius or 298 Kelvin. So when the entropy change is measured under these conditions, we call it standard entropy values. So that's what we call standard molar entropy. We measure entropy change under standard conditions. And part of the standard condition, if the solution is involved, the concentration will be 1 mole per dm cube. So we'll have the standard entropy change when we measure the entropy under standard conditions. So we'll talk about standard molar entropy, which is the entropy of 1 mole of a substance in its standard state. When the entropy is measured under standard conditions. So these are different substances measured under standard conditions. These are the standard entropy values. We have different substances. You have the diamond, the graphite, calcium, lead, calcium oxide, methanol, water, carbon dioxide, oxygen, ammonia, and the rest. So these are the standard molar entropy values for different substances. So we're looking at generalization of entropy. We talk about entropy, that entropy is a measure of the degree of disorderliness or randomness of a system. So we want to look at, certain things on entropy, generalization on entropy that we have to know. Generally, gases have higher entropy values than liquids, and liquids have higher entropy values than solids. We say entropy is a measure of the degree of disorderliness or randomness of a system. Now, if you look at solid, liquid, and gas, the arrangement of particles in solid, the particles are closely packed together. They cannot move from one point to other. They only vibrate about their fixed position. So entropy is relatively zero in solid. Entropy is extremely low in solid. Then we'll talk about liquid. The particles are free to move, but they are still held together by intermolecular forces of attraction. So entropy in liquid is moderately high. But in gases, entropy is highest in gases because the particles are in constant random motion, colliding with themselves and also with the walls of the container. So the degree of disorderliness or randomness is highest in gases. Kinetic energy is very, very high. So there are exceptions to this. We'll talk about solid, liquid, and gas. So entropy increased from solid, liquid to gas. So we want to look at certain exceptions. There are exceptions to this. For example, calcium carbonate, which is solid, has a higher entropy value than mercury, which is liquid. These are the exceptions. And please, we need to know this. These are few exceptions, which are the generalization of entropy that we're talking about. Another exception is simpler substances with fewer atoms have lower entropy values than more complex substances with a greater number of atoms. So the higher the number of atoms, the higher the entropy value. The fewer the number of atoms, the lower the entropy value. For example, calcium oxide has an entropy value of 39.7 joule per Kelvin per mole. But for calcium carbonate, the entropy value is 92.9 kilojoule per mole. The calcium carbonate have more atoms compared to what? Calcium oxide. Another example is carbon monoxide has a lower entropy value than carbon dioxide. So these are few exceptions that we need to know when it comes to what? Entropy values. That the fewer the atoms, the lower the entropy value, the more the atoms, the more the entropy value. So we're still going to look at other exceptions and other generalization of entropy. Please, I want us to take note of this. So still on the exception, for similar types of substance, harder substances have a lower entropy value. For example, diamond has a lower entropy value than graphite, and calcium has a lower entropy value than lead. So please, I want you to take note of these few exceptions. But when we talk about entropy increases during changes in states that give a more random arrangement of particles, like solid to liquid to gas. So when any substance changes state from solid to liquid to gas, its entropy increases. Like melting and boiling increase the randomness of particles. So there's increase in entropy, energy is spread out more, and the entropy change is positive. When we have increase in entropy change becomes positive. But when there's decrease in entropy change becomes negative. The diagram before us is to illustrate processes that brings about increase or decrease in entropy. Now there's a change of state from solid to liquid and liquid to gas. So if you look at the first illustration, solid to liquid, there's an increase in entropy because there's an increase in the measure of degree of disorderliness or randomness. Then from liquid to solid, which is freezing, there's a decrease in entropy, decrease in the measure of degree of disorderliness or randomness of the system. So entropy change becomes negative. Then if you look at from liquid to gas, there's increase in the entropy of the system and also there's increase in the entropy of the system. So there's an increase in the measure of degree of disorderliness or randomness. So there's an increase in entropy. Entropy change becomes positive. Then from gas to liquid, there's a decrease in entropy, decrease in the measure of degree of disorderliness or randomness of the system. So entropy change becomes what? Negative. So these are some of the processes that brings about changes in entropy, increase or decrease in entropy. So we can say entropy change is positive when there's an increase in entropy, and entropy change is negative when there's a decrease in entropy. So these are typical examination questions for us to consider. These are exam questions. So let's look at some of the questions based on what we've treated. Explain the difference in the entropy of each of the following pairs of substances in terms of their state and structure. Then A, look at bromine. Bromine is liquid and iodine is solid. So the entropy value for bromine is higher than the entropy value for iodine, because in bromine, which is a liquid, there is a higher degree of disorderliness or randomness. So entropy value will be higher in bromine as a liquid compared to iodine, which is a solid. Then B, hydrogen gas and methane gas. The entropy value for methane is higher than the entropy value for hydrogen. Methane has more atoms compared to hydrogen. Hydrogen have fewer atoms. So the more the atoms, the higher the entropy value. The fewer the atoms, the lower the entropy value. That is the reason methane gas have a higher entropy value compared to hydrogen. Then C, mercury is liquid while sodium is solid. So in liquid, there is high degree of disorderliness or randomness of the system. So the entropy value for mercury as a liquid will be higher compared to the entropy value for sodium, which is solid. Then D, sulfur oxide is a gas and sulfur oxide is liquid. So the entropy value for sulfur oxide, which is a gas, will be higher because there's high degree of disorderliness or randomness in gases compared to liquid, which there's low degree of disorderliness or randomly. So please, I just want us to attempt as many questions as possible. Feel free to reach out to me if you encounter any difficulty. I'm Mr. Joseph, your chemistry teacher. Subscribe to my YouTube channel, share, like, and reach out to me if you encounter any difficulty. Thank you for listening. I'm Mr. Joe, your chemistry teacher. Please don't forget to subscribe to my YouTube channel. Thank you very much for listening. Subscribe to my YouTube channel, Mr. Joe.